Wait, this was the program I wrote. It simply stores 3.3 in a floating point variable and prints it with 8 digits after the decimal point. So we would expect the output to be something like this. But instead, we get this. That's definitely not what we expected. So, why did the computer change 3.3? Or did it? Let's see. We all know that everything inside a computer is ultimately stored in binary, and the number 3.3 is no exception. But that raises an interesting question. How do we even write 3.3 in binary? If you have watched my previous video, we derived the decimal to binary conversion algorithm from first principles. Today we are going to extend that same idea to numbers that have fractional part in them. In the previous video, we represented 13 as this, formed an equation and solved it for a, b, c, d and e. Today we will represent 3.3 as this. The only new thing we need to understand is the place values after the binary point. Just like in the decimal number system, where the place values after the decimal point are negative powers of 10, in binary number systems they are negative powers of 2. Using this, we can write this equation for 3.3. Notice that the integral part and the fractional part appear independently in the equation. This means we can split it into two separate equations, one for the integer part and the other one for fractional part. The integer part is exactly the same problem we solved in the previous video. So let's focus only on the fractional part. So here we have our fractional part equation, but we are back to the same problem. One equation, infinitely many unknowns. We need to come up with an idea to solve. What if we multiply the entire equation by 2? Now compare the integer parts on both sides and separately compare the fractional parts. Immediately we get the value of alpha. And what's left is another equation of exact same form. Let's do it again, and again, and again. It doesn't seem to stop. And after a while, the binary digits start repeating a pattern. And that answers the question we started with. The computer didn't change 3.3. The binary representation of 3.3 never ends. So a floating point number has no choice but to cut it off after a finite number of bits. And that tiny approximation is exactly what we saw 3.2999995 instead of 3.3. But this isn't something unique to 3.3. In fact, there are infinitely many numbers that floating point numbers cannot store exactly. So how can we tell whether a number can be represented exactly in binary? This is a simple test. If you can find some integer n such that 2 raised to power n times of the number is an integer, then you can represent that number exactly in binary. Otherwise, its binary expansion goes on forever. And with that, I'll end the video here. Thanks for watching. See you in the next one.